Welcome, PCS members and friends, to our today's PCS IBS seminar. It is a great pleasure to have with us today Dr. Denis Kurlov from University of Basel and Russian Quantum Center. And I would like to invite our scientific host, Dario, to introduce our speaker. Please, Dario.
Yeah. Thanks, Dylan. Yeah, it's a great pleasure to have Denis today among us. Let me introduce a little bit his CV. So he got his PhD in 2019 from Amsterdam. After that, he immediately became a permanent researcher in Russian Quantum Center. So he moved to Russia for that appointment. But then starting from probably last year, I think, he added an extra position in University of Basel, where he's now working, although he's still keeping the position also in Russia. His research topics are, let's say, in quantum many-body physics, like many of us, and he worked on several topics, including also, let's say, localization and other things related. He's also a collaborator of our, let's say, good friend, Boris Altshuler. And today he's going to talk about AGP, Adiabatic eigenstate deformations, which is a topic that here in IBS we like quite a lot in the last year. And now I leave Denis to start. So please, Denis.
Yes, thank you very much, Dario, for the introduction. You hear me well, right?
Yes.
Yeah, perfect. So I also would like to thank you once again for inviting me. It's a great pleasure, and I'm happy to give a talk at your seminar. So indeed, today I would like to tell you about weak integrability breaking in the Heisenberg chain and what role this adiabatic gauge potential plays in this story. So this talk is based on two of my recent works, which were done in collaboration with Vladimir Gritsov from the University of Amsterdam and some of our students, either from Amsterdam or from Moscow at that time. So what I would like to tell you today can be split into two parts. In the first part, I would like to very briefly introduce you, well, not introduce, but discuss the topics of integrability, breaking of integrability, and chaos. Right, so I'll tell you about strong and weak integrability breaking, how you can quantify this degree of integrability breaking, and I will also introduce the adiabatic gauge potential, which can serve as a remarkably sensitive probe of chaos, of integrability breaking. And then we will move on to the second part of the talk, where the plot kind of goes as follows. We will first review a conjecture made by me and Vladimir Gritsov about the so-called quasi-integrability of the Heisenberg chain, weakly perturbed by a certain perturbation. I will introduce you to the concept of quasi-conserved charges, so approximate integrals of motion, basically. Then we will test this conjecture using basically a adiabatic gauge potential. We will see how it behaves for this kind of perturbation. We'll see that the behavior actually drastically differs from strong integrability breaking perturbations, which induce genuine chaos in the system. And then we will finish the talk with proving this conjecture analytically and showing that indeed this model, this weakly perturbed Heisenberg chain, can be viewed as a almost integrable model. But first, integrability and its breaking. And let us first very briefly discuss the case of classical systems. So in classical physics, what do we mean by integrable system? So if we have a Hamiltonian and it's integrable, then there are very many integrals of motion, so as many as there are the degrees of freedom in this Hamiltonian, and the Poisson brackets of the Hamiltonian and these integrals of motion vanish. Right. So due to the presence of this very many of this large amount of integrals of motion, conserved quantities, the phase space trajectories are confined to certain subregions, certain invariant tori. You see this, I represent them by these donuts. And the motion in the phase space along this tori is quasi-periodic. Now, the situation is completely different for chaotic systems. So for them, there are no invariant tori. The motion in the phase space is ergodic. And most importantly, phase space trajectories are exponentially sensitive to initial conditions. This is a crucial point for understanding classical chaos. So let us illustrate this on a paradigmatic example, namely dynamical billiards. What you see here are two billiards, two snooker pools, if you wish. Inside each of them, there are two balls. So they sit on top of each other at the moment, and they have very, very close initial conditions, right? So the positions are the same, but the initial velocities for these two balls, they differ by a very small perturbation, right? It's 10 to the minus 3. So what happens if we let these two systems evolve? Now, at first, you see that two balls basically go along the same trajectory. And on the left-hand side, for this rectangular billiard, this, this continues like that. However, on the right-hand side, you can see that, things already went bananas. And this is precisely what is the exponential sensitivity of phase space trajectories to the initial conditions, right? So if we let those two systems evolve for some time more, we will eventually end up with these two very distinct pictures, right? So here you see a very irregular pattern, whereas on the right-hand side, you see that two trajectories which started basically identically ended up in a completely different way. So what we see, this spaghetti on the right-hand side is basically the chaoticity, right? So mathematically, these two systems are conservative. So the total energy in both cases is conserved. However, on the on the left-hand side, each projection, so px and py squared, are separately conserved. And for this reason, the chaos does not occur on the left billiard, so it is integrable. It has more integrals of motion, right? Now, geometry.
Denis,
yes.
Excuse me. We have a question. Aura Entin-Wollman has a question.
Yes, please. As long as you have a question, please go ahead and interrupt.
Okay, so my question is simple. Why do you need the change in the initial conditions? What will happen if you don't have this little change in the initial conditions?
Then they will always, the two trajectories will always be on top of each other because it's essentially the same trajectory, right?
Okay.
However, this tiny perturbation leads to completely different scenario in integrable and chaotic. Yes, thank you very much for the question. So,
and also, sorry, Alexei also had a raised hand. Alexei, did you have a question?
No, actually, I just noticed that Aura had a question and no one seemed to have noticed, so I wanted to, yeah.
Okay.
So I suggest that you just interrupt me and ask your question right away. So geometrically, the right-hand side differs from the left-hand side by the fact that these edges are kind of, they are rounded, but very drastically rounded. What happens if we just chop off a tiny bit of this corner? Will we end up with a picture like on the right-hand side? Well, the answer is yes, but obviously it will happen after a very, very long time. because here on the left-hand side, as long as you do not hit this deformed corner, the situation will remain as if the system is integrable. So this is what we call a weak perturbation, right? And in classical systems, this phenomenon of weak integrability breaking is actually pretty well understood, at least for systems with a sufficiently small number of degrees of freedom. And this is described by the renowned Kolmogorov-Arnold-Moser theorem formulated back in the 1950s, which very roughly speaking states that sufficiently weak and smooth perturbations do not destroy integrability completely, because most of those invariant tori, they just get deformed, right? So squeezed maybe or something else, but they do not disappear. Some of them maybe do, some of them maybe vanish, but most of the invariant tori remain in place, and this leads to the system being almost integrable and stable for very, very long time, right? And this is basically one of the reasons why we can live on this very nice planet, and gravitational interactions between planets and the solar system do not, well, haven't led to chaos, at least yet.
Denis, we have a question from Alexei.
Yes, please interrupt and ask your question.
Yeah, this is probably more of a remark. I always thought that the Kamm theorem, it definitely works, but once you go to many particle systems, the strength of the perturbation where this still holds reduces drastically, if I remember correctly.
Yes.
So again, for solar system with, let's say, 9 planets, if we stick with the classical view, that's probably still working. But I think the estimates were that for some systems where mathematicians managed to put bounds, it went down super exponentially, if I remember correctly. So
yes, I thank you very much for the remark. I absolutely agree with this, and this is why I made a short disclaimer that at least for systems sufficiently small number of degrees of freedom, this holds and works. But indeed, even for classical many-body systems, there are strong, large problems. However, this is not the direction we want to proceed in this talk. Instead, we want to move in a perpendicular direction, if you wish, in the direction of quantum systems. And extending Kamm theorem to quantum systems is a very long-standing problem. I assume that it has, well, the first attempts occurred already around this time. So far, quantum analog of Kamm theorem hasn't been formulated, and I will not formulate it in this talk either. But I hope that by the end of the presentation, I will convince you that some certain small steps in this direction, well, can be made and have been made. Right. So let us now move on to quantum systems, integrable and chaotic quantum systems. Just to set the terminology, by an integrable quantum system, I mean a Hamiltonian, which possesses, again, a large number of conserved quantities or charges. So the commutator of those charges with the Hamiltonian and with one another is a 0. And the very important remark, those charges are local, right? So they can be written as a sum of some local operators acting on a finite number of sites. Now, if you do not make this restriction, then basically any finite dimensional quantum system would be integrable, because you can always just take projectors onto the eigenstate, and then the first two conditions here would be automatically satisfied. However, in the real space, for instance, those eigenstate projectors are highly non-local, and this is not what we want here. We need local conserved charges. Right. So if we have them, then actually there is a very important operator, the so-called boost operator, And this is not a typo here. It's actually like a first moment of the density of the second charge. And the second charge, by convention, is the Hamiltonian itself. So it's Q2J is this Hj. Now, this operator is very important because it acts as a ladder operator in the space of conserved charges. So if you commute the m's charge with the boost operator, even though this guy is not extensive, the result will be extensive. And amongst some terms, there will be the next conserved charge. So you can iteratively generate the whole family of conserved charges. Now, again, just like in the classical case, the presence of those conserved quantities severely restricts possible dynamics of the system, and it basically prevents the system from thermalizing. Now, in other words, if you prepare the system in a certain initial state, you can always retain the memory about it. By some local measurements, you can always check what was the initial state, roughly speaking.
Sorry, Denis.
Yes.
Now, M is running over the system sites or the Hilbert space? I mean, here you are dealing with single particle problems, many body, or no? Here you are dealing with the many body, right?
These are many body. Yes, these are many body.
So right. M is, I mean, the M is running over what? Over the system sites, or?
So it's of the order of system size. Yes.
Not of the Hilbert space.
No, yeah, it's should be of the order of system size. Yes.
Okay. And related question. I remember that. I mean, it's not my topic, so I could say something completely naive. But I remember that we had a talk that was explaining that, let's say, Bethe-Ansatz integrable systems don't fall in this category, if I remember correctly. I asked some other of the PCS members to, let's say, confirm or disprove what I'm saying. Do you?
So Bethe-Ansatz, well, I would say that Bethe-Ansatz solvable systems are exactly those which I'm talking about.
I see. Okay, so probably.
So, but maybe after the talk we can discuss it in more detail. Maybe.
Okay.
Maybe you mean something else. But,
okay.
Yeah, if I can join, because the question I had was exactly this. So actually, the person. So we had a lecture by Emil Yusbashian, who kindly lectured us a bit on the basics of integrability. But this was exactly my question. To the best of my understanding, while in classical systems, they although I don't remember the details, but integrability is, so to say, there's no ambiguity. There's only one way you can define integrable systems. While to the best of my understanding, in quantum case, you don't have that. So this is just what people assume is an integrable system. It's the case where you have a lot of conserved quantities, typically scaling with the system size.
This is true, yes. So this is one of the reasons why quantum CAM theorem hasn't been formulated, I believe, because the very notion of quantum integrability is less straightforward than in the classical case. However, what I'm showing on this slide is, if you wish, the most commonly accepted definition of quantum integrability. Yeah, and it's one of the most natural ones, right? Because there's a connection between conserved charges and integrals of motion.
Right, but let me perhaps ask one more question. So, sure. Does it make sense to chase after the generalization of the CAM theory? Because we know that for many body particles, it's let's say its utility is severely reduced because the perturbations for which it's valid would be so small that experimentally, say, it would have no consequence.
Well, this is roughly what we will see in this talk, actually. Well, you may not call it an extension of CAM theorem, but the question of dynamics of weakly perturbed quantum systems is a quite important one. Moreover,
I'm not saying that's not important. I'm just saying that COM is probably not describing the regime which might be experimentally or even analytically accessible for perturbations that are small, but not so small that COM works. That's what I was trying to say.
Right. Yeah. Maybe quantum many-body systems indeed. Well, as you said, because even in the classical case, COM theorem is not so successful. Maybe we shouldn't call it really extending COM theorem. But regarding, the finite size, nowadays, for example, quantum processors are really small, I would say. So even if you can get some bounds, which will give you basically zero perturbation strength in the thermodynamic limit, it can be of some experimental use, right, for quantum processors, for example, to see if the processor operates in the chaotic regime or not, because you don't want the processor to be in the chaotic regime.
No, that I agree. Just two more remarks before I. So one is there actually. This is a side remark. I just wanted to point out that there are systems where projectors on the eigenstates are actually local, although probably not in the many-body case. That's one thing, and another thing, I'm actually feeling bad that our director is not around. He's unfortunately on vacation this week, but he's actually actively working on a thermalization of weakly non-integrable classical systems beyond the COM theorem.
Yeah, well, it's indeed. Thank you very much for the remarks. To some extent, it's unfortunate that he's not here, even though I hope he has a very nice vacation. Yeah, about the projectors, indeed, but generically, they would be highly non-local, especially for the many-body systems. So that's why you should always make this remark that the conserved charges are local.
Yeah.
All right. So let me now speed up a little bit here. So these integrable systems can be described by the so-called generalized Gibbs ensemble, which basically differs from the ordinary Gibbs ensemble by including, all these extra conserved charges. And as I said, their presence prevents the system from thermalization. However, if you perturb the system and break the integrability, then generically, you would expect the system to thermalize. So locally, local observables would relax to the values predicted by just textbook statistical physics. Okay, so we have quantum integrable systems and quantum chaotic systems. But if you give me some Hamiltonian and ask, is this an integrable or chaotic? Well, I may try to look for those conserved charges, but if I fail, maybe I just didn't look well enough. So it would be nice to have some kind of generic and easy to implement measure of chaoticity. And one of the most successful paradigms here is based on the random matrix theory developed by Dyson and others back in 1960s, I think. And in this random matrix theory, people have very convenient spectral measures of chaos. So measures of chaos which are based on the spectral properties of the Hamiltonians. So one of them, for example, is the level spacing distribution. Now, imagine that you have a Hamiltonian, with random entries, and you calculate the levels, the differences between adjacent energy levels. And you calculate probability density for those energy level spacings. And then you will see that actually for integrable systems, this probability density, it's Poissonian, so this blue curve here. Whereas for chaotic Hamiltonians, you would obtain the Wigner-Dyson distribution, which is shown by the orange curve on this plot. And you can roughly understand it as follows. If you have an integrable system, there are very many quantum numbers which can distinguish the eigenstates. So it's not a problem to have the energy crossing, because if you have crossing energies, you can always distinguish the eigenstates by some other quantum numbers. So there are no correlations between the energy levels, which in other words means that there is a probability 1 to finding an energy crossing. On the other hand, for chaotic systems, energy is one of the few conserved quantities, and this introduces correlation between the energy levels, or as people call it, level repulsion, which means that there is basically zero probability to find energy crossing. Instead, you would see the energy repulsion. So this is all very nice, but unfortunately, this measure is very prone to finite size effects. This is especially the case if you have a very weak perturbation. So the chaos is not fully developed, if you wish. Then it's not really clear whether you have, well, you will never see a perfect Poissonian curve here. It will start somewhere, I don't know, maybe around 0.8, but it's generally hard to say if it's the effect of weak perturbation, weak integrability breaking, or just a finite size effect. So recently, people have developed an alternative paradigm to detecting and quantifying chaos in quantum systems, and it is based on the so-called quantum geometry, which is the study of well, geometrical questions in Hilbert spaces. For example, distance between the states, the distance between the density matrices, and so on. Now, this is a very fascinating field, but unfortunately, I don't have much time to talk about. Plus, I understand that you basically know this very well. So let me just introduce the tool which we will use in this talk, the adiabatic gauge potential. So you can define it as follows, right? Imagine that you have a Hamiltonian which depends on some parameter, and then there is an instantaneous eigenbasis which also depends on this parameter. Now, of course, there is a unitary transformation which connects those eigenstates at different values of lambda. And then the generator of these unitary transformations is nothing else but this adiabatic gauge potential. So let me then elaborate a little bit on the naming here. So it's adiabatic because it generates adiabatic transformations. It's a potential because, well, it kind of looks like a potential term in the Schrödinger equation. And it's gauge because there is some gauge freedom in this operator. For instance, it's defined up to certain operators which commute to the Hamiltonian. Now, you can easily derive the matrix elements of this operator, and you see that these are basically Berry connections. Now, to avoid accidental divergences here, because you have the difference between the eigenenergies in the denominator, we unfortunately have to renormalize it. Well, not renormalize, but regularize. So introduce certain small cutoff. And around 2 years ago, it was slightly more already. It was actually realized by Tolia Polkovnikov, Dries Sels, and others that the norm of the adiabatic gauge potential can serve as a remarkably accurate measure of chaos. So roughly speaking, the adiabatic gauge potential is a better measure than, for example, the level spacing distribution, because it takes into account not only the spectral data, not only the eigenvalues, but also the eigenstates. So it kind of knows more about the system. For this reason, it is also less prone to finite size effects, which is a good news. Okay, so as I said, the norm of adiabatic gauge potential can serve as an extremely sensitive measure of chaos. Now, you can easily understand from the eigenstate normalization, from the predictions of the eigenstate normalization hypothesis, that for chaotic perturbations, so if this V of lambda, so H naught in this talk is always integrable. Now imagine that V of lambda breaks the integrability of H naught completely. So you have a genuine chaos. In that case, the eigenstate normalization hypothesis applies, and you can show that this norm will scale exponentially with the system size and a certain non-universal coefficient here. However, and that was a intriguing finding of Sells, Polkovnikov, and co-workers for integrable perturbations. So namely, if this V of lambda does not break the integrability of H naught, right? So if the sum of two terms is also an integrable Hamiltonian. In the latter case, the AGP norm will be, well, its scaling will be polynomially bounded. So you can have a polynomial here, or maybe a logarithm. And well, this is very nice, right? Because exponential scaling can be easily distinguished from the polynomial one. I mean, numerically, it's absolutely straightforward. Even if you have relatively small system sizes, it's still very easy to do. And as an illustration, let me show you one plot from this work that I was referring to. What we see here, now I honestly don't remember which models these are, but this is not important. What is important is that indeed for chaotic perturbation, so this is a logarithmic scale, for chaotic perturbations, or in this jargon, in the chaotic direction, the scaling of the AGP norm is exponential, right? So for integrable system, it's some sort of a polynomial, or maybe a logarithm, I don't know, but it's not an exponential. And well, also an integrable, but kind of a trivial integrable case is free theory. In this case, the AGP norm will be essentially independent of the system size, and you can actually calculate this analytically. Okay, so now what if the integrability perturbation is extremely weak, okay? Will we have something else here? Will the scaling of the AGP norm be different?
Dennis, I don't remember the detail. In the chaotic case, is there any difference if the initial Hamiltonian is already chaotic and you, I mean, because in AGP you always have to do a perturbation already to start the machinery. So is there any difference if your original Hamiltonian is integrable and you perturb to make it fully chaotic, or if the original Hamiltonian is chaotic and you perturb with, of course, a chaotic perturbation? So do you distinguish the two or not? I don't remember anymore.
I think no, but it's also not so interesting, I would say. If it's chaotic, it's chaotic. So
no, but suppose that you have a system that is integrable, but you don't know what are the directions that preserve the integrability. So you could, let's say, misunderstand.
Yes. So as far as I understand, as far as I remember, if H naught is chaotic to begin with, you will always see this exponential scaling right away.
Right, but so when you see the exponential, you cannot guess, you cannot distinguish if it is H naught already chaotic or H naught integrable, and you found a direction that that is not the right one. Am I right?
I think so, yes.
Okay.
Well, maybe you can play with, maybe you can understand this from the coefficient in the scaling, but I think this has not been studied. So in this talk, I always assume that H0 is integrable because I want to break integrability. So I assume that H0 is well understood and it's integrable. All right. So as I said, what I wanted to answer is, will the picture be different if the integrability breaking perturbation is weak? And let me elaborate a little bit on what I mean by weak perturbation. So I will assume that the perturbation is linear in the coupling constant. And by the way, why this is important? Now, for example, you may ask, what will happen with this system, with this small integrability breaking perturbation? Will it thermalize? So the naive answer would be, well, yes, of course, because Fermi's golden rule tells us that there's a matrix element squared, so the thermalization time will be of the order of 1 over lambda squared. And well, in most cases it will be. However, if this perturbation is weak, then the thermalization time will turn out to be much, much longer. So, as we will see shortly, if the perturbation is weak, there are the so-called quasi-conserved charges or approximately conserved charges, right? So these are the operators this QM lambda, which commute with the total non-integrable Hamiltonian up to corrections of the order of lambda squared. Okay, so this guy is linear in lambda, but the commutator has only terms of the order of lambda squared. Now, in that case, the presence of these approximately conserved charges actually pushes the thermalization time into much longer times. Actually, you may cook up some special Hamiltonian, in which case this will be actually exponentially large. But this is really a fine tuning. What is important for us is that if you have quasi-conserved charges, then the thermalization time doesn't follow from Fermi's golden rule, and it is much, much larger. Okay, so now let us be more specific and discuss the perturbed Heisenberg chain. Okay, so by H0, now we mean the XXX Hamiltonian, so spin 1/2 isotropic Heisenberg chain. And as a perturbation, we take a very similar Hamiltonian, but it acts on the next two nearest neighbors.
Dennis, sorry,
yes.
I have a quick question. So when you're talking about the perturbation, you're working at small but finite lambda, is that correct?
Yes, exactly.
So you're computing the AGP for lambda that is, so you consider some perturbation V1, but lambda is finite.
I will do both.
Ah, okay.
In a couple of slides, I will show you both.
Okay, thanks.
Yeah. Yeah, so H0 is integrable. It's actually the first model in the world which was solved by the beta ansatz. So Hans Bethe invented this method playing with this Hamiltonian. So it's a very famous model. And this perturbation is also very interesting because it was noticed already in 2006 by Achim Roche and co-workers that, well, for non-zero lambda here, if you have this next to nearest neighbor exchange interaction, then the thermalization time is actually much larger than follows from the Fermi's golden rule. Now, we now understand that this must be due to the presence of those approximately conserved charges. Actually, they also understood. So for zero lambda, we have exactly conserved charges. For example, the simplest one, the simplest non-trivial one is this. everything is SU2 invariant here because obviously both the Hamiltonian H0 and the perturbation are SU2 invariant. So it turns out that for non-zero lambda, you can somehow deform these guys in such a way that they will commute up to corrections of the order lambda squared, and this will result in this anomalously long thermalization times. Right. Well, this is what I just said, but how do you find these deformations? Well, you make an ansatz that, you take the initial...
Sorry, again,
Yeah.
a quick question.
Yeah.
So, but if you
Please
consider
go ahead.
a generic integrable system and you had a perturbation, can you always find such quasi-conserved quantities, or?
No.
Okay, so you cannot, not even to, if you request, well, even if you request instead of O lambda squared, you would request just lambda. That.
Oh no, if you request O lambda, then this will always work.
All right, because that would be the order of the perturbations of, yeah, right, thanks.
And in that case, Fermi's golden rule will work. You will end up with the usual case.
But okay, given that, can you actually invert it and identify which perturbations for a given Hamiltonian would lead to quasi-conserved quantities and which don't?
Well, this requires a lot of work, so I don't have an immediate answer. By the end of the talk, we will have something along these lines, but not entire. So it's like, yeah, please.
Yeah. Yeah, I mean, the fact that it requires a lot of work to me is an answer.
Yeah, well, it's like in Kampf theorem for sufficiently smooth and weak perturbations. Now there is some kind of requirement of being sufficiently, I don't know, smooth. Well, actually, it looks like it has to be sufficiently local. So let me just jumping ahead. If you take a perturbation which is sigma j plus 3, for example, then this will not work. So there are no quasi-conserved charges for the Heisenberg chain perturbed by a less local exchange interaction. So it seems to be a special feature of this next to nearest exchange perturbation.
Okay.
Yeah. Now, this dumbest way to find these deformations is to just calculate the Hamiltonian and the commutator and require that the linear term vanish. Well, this is what actually we did some time ago, 2 years ago. We made an ansatz for those deformations. It doesn't matter the details. It's just a dumb brute force that you take sort of the most general ansatz consisting of SU2 invariant spin polynomials, and you try to solve these operator equations for those coefficients alpha k. And actually, you can take the most general ansatz. So if you are unable to find those coefficients, you can safely say that there are no quasi-conserved charges. This is what happened with sigma j plus 3. However, for this perturbation, we were able to do so. And together with Savas Malikis, who was a student of Vladimir Gritsev at that time, we constructed the first 6, I think, quasi-conserved charges for this perturbed Heisenberg model. So for example, if the exact charge looked like this, sigma j cross sigma j plus 1 dot sigma j plus 2, so for the deformation, you would have a similar structure, but you would increase the support. So this acts on more sides, and you introduce some holes, kind of. Yeah. So we were able to find a couple of first quasi-conserved charges, and well, it's a brute force, so you cannot continue forever. But it was very tempting to make a conjecture that actually there are as many quasi-conserved charges for this model as there are the exact charges for the original model, unperturbed model. Yeah, so this was the situation some time ago. This paper took extremely long to get published for some reason. Yes. So this I will probably skip for the sake of time, but you can do the same thing for XX model. So not the SU2 invariant case, but just isotropic XY model. We studied this model in a completely different context. Well, basically many-body localization in this model, but we realized that same story applies, and you can construct quasi-conserved charges. And the structure, the structure of the perturbation is very similar. It's same interaction, but larger support. Okay, so here is the conjecture, and now, as I promised, let us test it with the help of a adiabatic gauge potential. Right, so this is the Hamiltonian, and we calculate this thing for a finite lambda. And well, this is what we see. I remind you that for integrable perturbations, we would always see polynomially bounded scaling. For purely, genuinely chaotic perturbations, we would always see like an exponential scaling starting right away. What we see here is different from both cases, from both integrable and purely chaotic cases. What we see here is that for a given lambda, up to a certain system size, the scaling is such as if the perturbation preserves integrability. For larger system sizes, actually the exponential scaling takes over. And, for different lambdas, this occurs at different system size. So you can invert this logic and say that for a given system size, there is a critical coupling, which is system size dependent. And then for coupling constants smaller than this critical value, the scaling is polynomially bounded. Well, in our case, we have a logarithm. I actually don't know why it's not a polynomial. This is something I do not yet understand. But it's most importantly, it's polynomially bounded. However, if you take a perturbation with the coupling constant larger than this critical value, you will obtain an exponential scaling. Okay, so interestingly, this critical coupling is exponentially small in the system size. So this is going back to our discussion about failure of classical CAM theorem for sufficiently large systems. Here we kind of see a similar behavior, similar situation, but as I said, it still can be used as giving a bound on the chaoticity for finite systems, and this can be of great interest for field of quantum computing, for example. So if you remember anything from this talk, please let it be this slide, because this is one of the most important slides in the whole presentation. It shows you that for a weak perturbation, for which there are quasi-conserved charges, the AGP norm scales in a distinct way from chaotic or integrable perturbations. Now, maybe our conjecture was right. Maybe this system is indeed very special, and maybe we can construct even more quasi-conserved charges. Before we proceed with quasi-conserved charges, let me show you that indeed, if you take less local perturbations, so sigma j plus m, where m is larger than 2, you immediately obtain, and this is now picture calculated at lambda equals 0. So the eigenstates here are those for the unperturbed model. You immediately obtain, for less local perturbations, you immediately obtain exponential scaling. However, for this special case of next to nearest exchange interaction, remember lambda equals 0 for the AGP, you have this polynomially bounded scaling. So if you wish, this is the prescription of how to distinguish genuinely chaotic perturbations from the weakly chaotic ones.
Now, if I
Sorry,
understand
one
correctly,
Yes.
No, go on, Dari.
if I understand correctly, now you don't have a way to distinguish an integrable perturbation from a quasi-integrable perturbation. I mean, it's really a matter of, let's say, numerical values, right? It's
Oh
not
no,
qualitative.
why? You may calculate at finite lambda, and then you will see this.
No, yeah, but wait. I mean, suppose that let's go to the next one.
Mhm.
Suppose that for m equal to 2, you have genuine integrability. So this is an integrable perturbation. Still, this AGP norm will grow, right? And not exponentially, of course.
Mhm.
But so I mean, in this plot, you couldn't distinguish if this is quasi-integrable or fully integrable. Do you agree?
Yes.
Okay.
In this plot, yeah, I agree, because this is for lambda equals 0. And
Exactly.
the reason of this plot is to distinguish chaotic from weakly
Quasi-integrable. Okay.
quasi-integrable. So I suppose that I know that the perturbation breaks integrability. I just want to know how strong it is.
Okay.
Now, if I don't know anything, then I just calculate the AGP at finite lambda, and then I see 3 different pictures for integrable, chaotic, and weakly chaotic, quasi-integrable.
Okay, got it.
Okay. Yeah.
Yeah, right. My question was, I realized so when you're adding the second nearest neighbor term, and you're saying that you can you constructed quasi-conserved quantities, and then you're saying whether one can construct more. I'm a bit confused because I had the impression that you basically already take all the charges you had in the integrable system, and you had a correction which gives the quasi-conserved quantities, and that's as much as you can hope for. But now, if I understood you correctly, yeah, go. Yeah.
Yes, but I only found those corrections for the first few charges. So I have this QMs, and M, I actually work here analytically in the thermodynamic limit. So M goes to infinity. I only found those corrections for M not larger than 6.
Okay.
So my conjecture is that for larger M, for higher order charges, I can also find those corrections, meaning that every conserved charge of the initial integrable model gets deformed into a quasi-conserved one. It's not just that, first, 10, 15 do, and all the rest just get destroyed completely. No, every conserved charge of the initial model can be deformed into the quasi-conserved charge of the weakly perturbed model. This is the conjecture. And did I answer your question?
Yes, I think because on the slides, from the slides, I had the impression that it was constructed for all M. That's why I was confused.
No, yes, I should maybe.
Okay, I missed this part.
I should have stressed it. But yes, this is the situation. Yes?
A question that I'm not sure is well formulated, so if it is not. Is there any hierarchy between these charges, like, let's say, small m influence the dynamics more and large m? No, they are all on equal footing, right? So
No, actually, you're right. The lower ones are more important, I would say.
I see. Okay.
Well,
well, the reason why I'm asking is because, let's say, I was wondering if your numerical results suggest that all of them, because, if they are all on equal footing, just breaking, let's say, the large M would be enough to destroy everything. But if they're not on equal footing, maybe breaking the large M will be not visible for large. I don't know. I'm wondering, if.
Yeah, yes, depending on what is important for what. For example, in the generalized Gibbs ensemble, I would expect that, the corresponding Lagrange multipliers for higher charges would be smaller and smaller, for example.
I see.
But still, they are non-zero.
Okay, yeah, as I said, I didn't, was not a well-posed question, but yeah. Okay, thanks.
Yeah, Dario, if I may comment, my guess is that, again, if you add a perturbation that is almost any perturbation would probably either break these charges altogether, or will, if there exist quasi-conserved quantities, they will exist for, I mean, all the charges will get deformed. Because I strongly suspect to engineer something that only a perturbation that on one hand, like say, keeps charge 1, 2, 3, gives them the quasi-conserved charges and breaks everything else. This would probably require perturbation. I mean, this probably is possible, but the perturbation would be very, very non-local and complicated looking. That's my guess.
Yeah, could be. Well,
unless you fine-tune the model itself, I'm pretty sure you can also design a model where things might look simple, but this would again require
right.
So generically, I think it's either all or nothing.
I agree that it's completely natural to expect that it's either all or natural, and this is what we sort of did back then. But this integrability game requires more rigor, sort of. So at that time, we didn't have a proof that you can actually deform all charges.
Oh, no, sure. This is more like a hope why you should follow and solve this issue. It's not a proof, it's just an intuition.
Precisely, yes. But I completely agree with the intuition, and I had an identical one. So actually, what I want to do now, and I should really speed up, I want to basically prove this conjecture. So we saw that this model is quasi-integrable in the sense that it has a few quasi-conserved charges that almost commute up to corrections of the order lambda squared, and the AGP norm behaves in a distinct way for this perturbation. So there is indeed, as we just discussed, there is a hope that we can prove that there are as many quasi-conserved charges as there are exact ones for the unperturbed model. Okay, so in this slide, the most important thing is that the AGP norm, A lambda, it satisfies this operator relation, where this term f of lambda is a certain operator which commutes with the Hamiltonian. So it's diagonal in the eigenbasis of the full Hamiltonian h of lambda. It can be derived very easily, but just for now, it's important that this relation exists. Okay. Now let us do a trick. Let us assume that the perturbation preserves integrability. So h naught was integrable. We included h of lambda, and h of lambda, full Hamiltonian, remains integrable. So for the original Hamiltonian, we have unperturbed charges. And if we assume that this guy is also integrable, there are certain deformations of initial charges which are also exactly conserved. And as we just saw on the previous slide, this Hamiltonian satisfies this operator relation with a certain obvious initial condition. Now, recall that the Hamiltonian is a conserved charge itself. It corresponds to the conservation of energy. So it's natural. The question is, what are these charges? How these deformed charges are related to the initial ones? The deformed Hamiltonian is related to the initial one via this relation. So the AGP generates this deformation. But since the Hamiltonian is a charge itself, let us try a similar deformation for the QM. Okay. It's this relation. Now, this operator is again, it's a gauge freedom, kind of, it's an operator which commutes with this charge and therefore with all other charges. So we can actually write it as a linear combination of these charges, which we do not know yet. Now, actually, from this relation, you can easily prove that these deformed charges indeed commute, which means that our ansatz for this relation is consistent. We started from, we assume that those charges commute. We assumed that they satisfy this relation, and everything is consistent. Very nice. But does it mean that any perturbation V can result in commuting charges? Well, yes, but doesn't mean that it's integrable, because as we discussed in the beginning, sometimes those charges are extremely non-local, and this is not what we need. So the bottom line here is that this equation has a solution for local charges, which can be written in this form as a sum of some local operators, only for specific choices for the adiabatic gauge potential, which in turn means only for specific perturbations V. Okay, and what are these smart choices of the adiabatic gauge potential? Well, it turns out that this question has been answered by these people working in the context of ADS CFT correspondence, the deformed conformal field theories, so in high energy physics. Now, in this work, it has been shown that actually if you take these three, so it has been shown that there are three options for the AGP, which then solves you this equation for local charges. The first option is a local AGP, but this is kind of trivial because it can be just related to a trivial rotation of the basis. This is not a non-trivial deformation. The other two options are non-trivial. The first one is a boost operator, or if you wish, a generalized boost operator. So the initial one is defined in terms of the Hamiltonian density here, but no one forbids you to take the density of some higher charge. Now, it turns out that if you take the AGP proportional to this boosted charge, you will get a local solution to this operator equation. Now, the last option is a little bit more exotic. It's given by the so-called bilocal operator. Now, in the literature, there is this weird, slightly weird notation. This is not a commutator. It's just a definition of an operator which is not local but bilocal. So you have here two summations, and the corresponding densities of two charges are defined on different sites here. Now, it can be also easily shown that the commutator of a local thing with this bilocal thing is a local operator, which again gives you a very nice solution here to local conserved charges. Okay.
Sorry, just to check whether I'm still following, could you go one slide, probably one slide back? Yeah. No, the slide where bilocal AGP was presented.
Yeah,
so I'm suspecting that if you try trilocal AGP, then you will get bilocal terms, and that would not be what you want.
Yes, I think so. Well, at least you will not get local terms.
Yeah.
Okay, so to summarize these two horrible slides full of formula, what we have is the following. There is an operator identity which you can solve for the exact charges which would commute with some Hamiltonian. Now, if you choose the AGP wisely. But how do you solve this? Now, I don't know. I have zero idea. And when I don't know, I do Taylor series, maybe formal Taylor series. This is what we have here. Well, let's expand everything in the powers of lambda. And plugging in these expansions, these formal expansions into this equation 1, we obtain a relation, well, a bunch of relations, which we can now solve iteratively, order by order, and reconstruct this conserved charge. If we do this for all this infinite number of terms, we will end up with the exact conserved charge, which commutes with this extremely complicated Hamiltonian. Okay. However, if we truncate everything, if we truncate the Hamiltonian, for example, to the first order of in lambda, and also this relation, we will actually obtain exactly those quasi-conserved charges, which do not commute with the Hamiltonian exactly, but only up to some higher order corrections. And this is what remains to be done. You have this relation. Now, you have a Hamiltonian with a very small perturbation, which is linear in the small coupling constant. Then you truncate this relation. And now, if you recall that for n equals 2, this relation gives you the, well, you have Hamiltonians because Q2 is the Hamiltonian. So it gives you this relation. Actually, from this relation, for a given perturbation, you can find the corresponding AGP to the linear order. And essentially, if you can do this, then this V1 is weak perturbation. So it does not break integrability completely. So if there exists an AGP satisfying this relation 2, then you can just go ahead and calculate directly from this relation for any n larger than 2, the remaining quasi-conserved charges. So this relation, again, gives you now an infinite family of quasi-conserved charges, not just the first 6 as we did by brute force, but as many as you wish, as many as there were exact charges for the unperturbed model. So as an example for this perturbed XXX chain, which we were discussing, this program works, and the AGP which you must take is the boost operator of the third charge of the initial XXX chain. So the bottom of the take-home message here is that it can be done for this perturbed XXX chain, and you can construct an infinite family of those quasi-conserved charges. Now, in turn, their presence leads to this numerically observed anomalous thermalization time, and also to this peculiar crossover in the scaling of the AGP node that I also showed you slightly earlier.
Sorry, another question. Going back to equation 1, but do you have a generic way to resolve? So knowing V1, is there a generic way to find A0, or you have to try some guesses?
Yeah, this is what I meant by requires a lot of work. You have this relation. If you can somehow find a way how you can, So I mean, I don't have an answer.
So basically, this commutator equation, it's basically you have to make a guess or have an intuition how the answer looks like. There's no systematic way to solve them.
Well, at least at the moment, I'm afraid there is no systematic way. Yeah, but at least there is an equation with which we can work. Well, and there are also not so many choices, right? You're not allowed to take arbitrary generators here, AGP. You may also only try among these basically 2 families. So you may try boost operators, you may try bilocal operators. So essentially, by plugging in certain linear combination of these 2 AGPs, you now must play with this equation and see if you can tweak the coefficients in the linear in the AGP in such a way that it's satisfied. So, still a lot of work, but more or less clear what you should try. But you still have to try this. Okay, so same can be done, just quickly, same can be done for this perturbed XX chain, but in this case, actually, the AGP is this, it has to be this peculiar bilocal operator. I'm not gonna go into detail here. Okay, so finally, I would like to mention a related work which actually appeared on the archive, like a couple of days before our, which dealt with same question basically, weak integrability breaking. Well, they did not study the AGP behavior in this weak integrable cases, weak integrability broken cases. However, they kind of considered higher order deformations. While we were only interested in linear in lambda perturbations. So these guys from Caltech, they allowed for higher order terms in the Hamiltonian, and then you basically do the same. You just do more iterations of this equation, and then you can find quasi-conserved charges, which also include higher order perturbation deformations. And by having this, you may actually increase the thermalization time even longer. But it's important to stress that in order to do so, you must also have all these orders of perturbation in the Hamiltonian. So in other words, if you have just H0 plus lambda V1, it's not possible to have more than linear terms in the charges, which is kind of natural because it would be then just the excess of accuracy. And of course, if you keep all orders here, as I said, you would end up with the exact charges. Right. With this, we come to conclusions or take-home messages. And well, to me, two most important things that I've said is that for weak integrability breaking perturbations, the adiabatic gauge potential behaves in a distinct way. And therefore, AGP can actually distinguish not only between integrable or purely chaotic perturbations, but it can also tell you if the perturbation is weakly non-integrable. Right? And this distinct behavior is is displayed as a sharp crossover between a polynomially bounded and exponential scaling. And essentially, if you observe this behavior of the AGP, then I suppose there must be quasi-conserved charges. And there is more or less an algorithmic way how to derive them for a given perturbation. All right, so with this, I would like to thank you for your attention. And thank you for having me here.
Thank you, Denis, for this excellent seminar. Let us thank Denis.
Thanks a lot. Are there any other questions, maybe?
Yeah, let me ask one, although I realize it's probably is irrelevant. I was just curious, in the classical case, the Heisenberg chain is not integrable, the 1D, but it's close to an integrable model, the Toda chain. I'm curious whether there's an equivalent of the Toda chain in the quantum case.
Yes, there is an equivalent of Toda chain in the quantum case, but I have not studied it in the context of integrability breaking perturbations.
Okay.
Okay, do we have any other questions from the audience? Seems not. So in this case,
probably discussed everything during the talk.
Yes, there were many questions and discussions. So then let us thank Denis again.
Thank you very much. It was a great pleasure to, talk at your seminar. Thanks again for inviting me.
Thanks for that.
Thanks for interesting questions and discussion. Great pleasure.
Yeah, can I still ask a question? I realized, actually, the question is, do we have the after seminar discussion?
Oh.
Unfortunately, not much, because in 15 minutes I have to give another talk, actually.
So probably
okay. So that's why I'm asking, because I realized probably there wouldn't be. So let me ask something I was keeping for. It's essentially one question we're interested in here. Dario would recognize that. So AGP is indeed a nice quantity, but it's global. So if you want to do the measurements, you have to compute the entire spectrum, which for quantum many-body systems might become a pain, especially if you need to go to larger systems. Did you consider any modifications, or were you thinking of some variation on AGP that allows you to extract similar information, but only with few states? So assuming you can sample typical states from the spectrum. So you sample one or two, well, few, not all.
Yeah, that's a great point, actually. Well, no, we only restricted ourselves to, the largest sector.
Yeah, because I can reveal a bit. We faced that problem. We are looking at a quasi-periodic system, and we tried to look at the energy resolved AGP. And Dario, correct me if I'm saying anything wrong. That proved to be quite challenging because figuring out the correct window size is a pain.
Yeah, because when you want to go to very large system sizes, you are restricted to just sample few eigenstates in an energy window of your interest. And somehow it looks that, let's say, AGP is highly sensitive to the choice of the energy window. So when you change the system size, become hard to make comparisons and so on for that reason. And yeah, if you want to go really to the larger possible sizes, and this is, let's say, relevant for, let's say, MBL and all these debates where really one size more is the important one.
Yeah.
This is proving to be a hard point to hit. So yeah, Alexei probably was wondering if you thought about that, but probably not really, right? Because
not yet. To be honest, I only started thinking about the AGP not so long ago. But yeah, I agree that there are a lot to add to AGP. To say the least, every time I look at the cutoff,
the cutoff,
my heart aches. Yeah.
All right, but that's sorry. I was actually, that was the question I missed from the very beginning. I was wondering. I mean, Polkovnikov and he has a subsequent paper, because after they introduced the AGP, basically the first thing they did, they tested it on the disordered Heisenberg chain, and there they suggested that you can avoid the cutoff by taking the log of the AGP and averaging that. So you fix an eigenstate and compute this
fidelity susceptibility.
Yes.
Yeah.
And they're claiming that this kills the accidental resonances as well.
Yeah.
Oh, okay.
So that's so that this you might consider using that. Well, at least it has good chances of working in your case.
Right. Thanks a lot. Yes, somehow I missed this point.
Yeah. Let me just at this point release the other spectators, and we can go off YouTube. So thank you all for coming, and who is interested, maybe a few more minutes, but not that much, depending on Denis. So thank you. Let's conclude the official